Hello. So I'm going to be talking about comparing biomechanical efficiency of humans and ants using kinetic energy analysis. So my first observation is that when I saw ants scurrying around on the ground like they do very quickly, I think about how if ants were scaled to the size of humans, they would be as fast as racehorses. And that got me thinking about how this is possible and whether the differences lied in anatomical features of the gait or physiological characteristics. And the implications of this inspired me to pursue a greater understanding of this ant locomotion in comparison with humans. So, firstly, there has been a lot of research on ant biomechanics because of how impressively they can achieve things such as lifting many times their own weight. Yeah, one paper that I looked at was Marianne 2021 that discussed how ants alter their gait to account for different loads. And that was really interesting. There are, however, very few research papers that actually discuss comparing the locomotion of an ant to the locomotion of a human. And I wanted to fill this gap. Um, so I wanted to take a biomechanical approach that relied on kinetic energy as opposed to a chemical analysis because it's much easier to analyze. You can just analyze a video and that's how it's done. So that's what I was going to be taking a look at. And this could have many applications from legged robot development to prosthetic limbs. So with this, my hypothesis was sort of based around the efficiency of an ant gait versus a human gait. And my hypothesis had two components. The first one being that the biomechanical efficiency of ant locomotion is greater than that of humans. And a second component, which is that the previous relationship explains the greater relative speeds attained by ants. And that will only be true if the first one is true. Now, okay, so I have a methodology foundation. This is sort of what I based my method off of. So it was necessary to define what variable I would be using for efficiency. And after some thinking, I came to the conclusion that I would be measuring output efficiency, or rather output energy of the organism, which is just the most basic motion, moving from point A to point B, and summing that with limb an isolated limb movement, which is if you're running on a treadmill, for example, all of your relative limb movements. I would be summing that energy with the basic energy. And that would give me total energy. Now I would divide that basic output energy by the total energy, and that would, in theory, give me a rough estimate of energy efficiency. And I was able to prove this mathematically. So yeah, that was what I chose. Now for the experimental methodology, so firstly I had to recruit a human volunteer, AKA myself. Um, I weighed myself on a scale and that was recorded. Then I actually made a reference scale and I taped it to a treadmill. I got on the treadmill and I just like increased the speed until I was at a comfortable walking pace. Yeah. And I measured my limb movements or yeah, with a video camera. I just recorded myself walking. Then I obtained a video from Reinhardt and Blickheim 2014 that depicts a carpenter ant running over a piece of graph paper, and that was very useful. I estimated the mass of each limb based off of Plagenhof 1983, the limb ratios, and that was for humans. I estimated my limb masses, and then I estimated the ant limb masses based on the given mass of the ant. I calculated the output energy, and that's easy, just speed times velocity squared divided by 2. I use the limb dimensions and masses to find the moment of inertia of each of the limbs. And then I like really closely analyze the footage at 8 of the primary gait phases. And I had to measure both angular velocity and linear velocity of the limbs. And then I used that and I converted it to kinetic energy. I then I summed them all together for each phase, and then I phase shifted them because I was only taking the data for one half of the body, the left half specifically, and I phase shifted it for the right half, and then I got the total energy at each phase. Yeah, due to the complexity of the analysis, because it took 6 hours for each sample, I had to only do one each, one of the human, one of the ant. Okay, so here is human gait compared to ant gait. This is me on the treadmill, and these are screenshots I took from the video. You can just see the video of that playing. You don't have to watch that. I guess you do. Okay, there. Here are my results, which I organized into a table. Yeah, they were pretty interesting. You see how and we'll go over that later. So we have basically for human efficiency is 83.3%, and then for an ant efficiency is 86.6%. Okay, so what was really interesting is that with the human, the kinetic energy of the limbs were pretty much synchronous, but with the ant, it was sort of all over the place. And this had to do with the tripod gait versus bipedal gait. So even though the first part of the hypothesis was correct, that ant efficiency was higher, it was not substantial enough to make any sort of noticeable difference in velocity or like movement velocity. But yeah, the reason why this occurred is though the ants had very light limbs, they had these extremely rapid movements, and because of the quadratic relationship of velocity and kinetic energy, that really sort of raised the average kinetic energy levels. Okay, so the main thing I would change was the process for analysis of the data, because that took a very long time. A friend told me about Locker Pro while I was expressing my woes And I think I might use that program for the analysis. Also, I think instead of using kinetic energy, I might use a work-based approach, which is more true to mechanical efficiency. Yeah, and here are my citations, and thank you.